Yeah, hello everyone. I'm very excited to be here and talk about cloud robotics. So I'm currently a fifth year PhD student at UC Berkeley. I have been working on cloud robotics for quite a few years. So I'm very excited to share the latest updates on the FogROS and FogROS2 that just like our lab have been developed. So let's get started. So I mean, just like everyone in the talk, I don't need to go through this slide. Literally, like what is cloud? But cloud is just basically some kind of computing resources that people can pay and then to use those kind of resources. And also just this is just like a background on just like wherever the cloud robotics notion that comes from. Actually, just I think this is come from different places, but the earliest I can find, and also like the most notable one is from James Kuffner's definition on the cloud robotics at 2015. I think it's just like from his definition, it's more like, oh, as long as it's networked, as long as like the components are from distributed resources, then we can call it cloud robotics. So I really like this definition because like sometimes we don't realize we are doing cloud robotics, but we are. So like, for example, like suppose we have a local Kubernetes cluster that is sitting somewhere, and we can also just use whatever knowledge we have in or we have developed for the cloud robotics to that area. So, and also just of course, just like cloud robotics have a lot of benefits, like it can just like give a lot of like resources from network, like multi-core CPUs, GPUs, to mobile robots that cannot be equipped with such kind of advanced hardware. And we have been working on this for a very long time, like since 2015. But still, just like I think before like we actually launched this FogROS2 like project, what we did earlier was just like one application at a time, just like moving grass planning to the cloud, then we just publish a paper. Moving motion planning to the cloud, we publish a paper. Then just like we realized this is totally ad hoc engineering, and it's not definitely not research, but we just enjoy publishing papers somehow. So that's why just like we just say, oh, like can we just put a framework together and just like with all the code together, just like basically the intuition is just like, oh, like suppose we have some kind of like scripts that create the cloud that is remote somewhere, establish all the connectivity stuff, and then just like all the application that you write in ROS can just like be moved to the cloud. And then basically it just works. And then just later we just like being more aggressive on just like building up our ecosystem. So we just became like part of the official ROS2 release by just like basically bumping our version to 2 and also supporting ROS2. And so like we are just official release of ROS2 Humble, basically a background of like robot operating system. So basically we have like ROS nodes and also like publish the script communication paradigm basically to connect the nodes together. And so basically what we do is to just move like some part of the ROS nodes to the cloud, but like and also like the workspace of the ROS2 also to the cloud, and also establish the communication. And we support a lot of cloud service providers. We also have like a bunch of features on like stream, like image compression, like supporting Kubernetes backends, like a lot of like integration, like things like Foxlove, of course Arvids, and also like command line interface, also to just like quickly interact with cloud as well. And also like the speed that we move after we move to cloud is also much faster. Like we have like 12x faster on like grass planning, and also like 45x like speed improvement on motion planning by just like giving robots a better hardware, because like essentially like for this kind of fetch robot, like hardware is very limited. I remember it's only 4 cores. So then we just like quickly, and also like this is something that people already know. It's just like we also have a ICRA like tutorial on like basically hands-on session on FogROS2 like this year. Basically, a lot of people just like sign up and work with FogROS2, and also Florence Cloud Reaper that he mentioned last time. So then we just also just like considering like those kind of like subdivision of the fields of like cloud robotics. It's not like just like we think about just cloud robotics framework as a whole, but they just like individual topics. We realize like the most difficult thing to do is the connectivity, because like obviously like ROS doesn't handle that very well. It's like, oh, like why does my robot does not connect with another? And it has like a lot of like complexity that we have to debug. Like sometimes we just figure out like, oh, like it's because like DDS version doesn't match or something. Like there are like so many things that can go wrong, and but still like because our like robot typically fixed with a specific like vendor or DDS version, and also sometimes like the network is very hard to just like just like tune. So that's why we think about just like having a framework that basically connects all the robots, agent, cloud, whatever. Like as long as just like you have the one machine and another machine, it which is happen to be a robot, they just connect. And of course, we want to make it to be like secure. So because we are just literally connecting machines like across public internet, we also want to be global. So like it can be peer-to-peer connection. So like you just like basically just like you don't have to specify like some like weird like things like IP address, and they just connect. And so what we hope to do like for the framework is like we don't need to configure the network, like no IP address involved, no code modification involved. Like it just like ROS2 application, it just works as a whole, no reliance on DDS, and also just we just work across different network domains. So I'm going to quickly skip like what I did, but essentially just it works through a peer-to-peer network, and also I'm going to just like talk about like the extension of this one later. So I can first show a quick case study of like the things that we considered before. So it's a distributed fleet learning, which basically just we have like a lot of robots across different places at like East Coast and West Coast, and also like learning server, and they just like span across different places. But we want to just like have them to just train a policy together. And so basically, we just want to just like reach this kind of like communication between different robots. And actually, we just like subdivided like two robots to, I mean, just like two robot arms to actually two robots. So it's actually four robots. So basically, like the four robots can just like learn this policy together by using our framework, and they just connect. And as you can see, we can also just like see just like Zoom session that it's sharing, and the robots are simultaneously to work together. And this note that we don't need any VPN, and it just works with any of the DDS, and also it just basically do some like launch file basically to attach our framework, and it just works. And we also have another framework that also use like the SDC. Basically, how it works is just a peer-to-peer network that basically connects the ROS node. So what we do is to just have this kind of like mobile robot. This is just like a mobile robot connect with the Raspberry Pi, and it scans the room. Basically, in this case, it's a shelf, and it builds up a 3D reconstruction of the scene. And later, you can just like search for objects within this 3D reconstruction. Like for example, if I want to search for a specific medicine, like magnesium, we can directly just like search for it by this mobile robot and also the cloud. We actually have this demo at IROS last year, a physical demo. If you guys like ever went to the booth, you could just like see our demo. A real demo, they basically we set up a shelf, and then just like the people go there and ask for stuff, and like our thing just like directly pops up. Oh, here's the thing that you're looking for. And of course, looking beyond, I think this is the main focus of the talk. I think previously it's just like background, because I think like a lot of concurrent work that I know of already built up this current stage, things like Zeno, like and also like a lot of like development from DDI side. So I'm really want to I'm very excited to actually talk about things that look beyond, like because like what is actually changed this year and also last year is large language models, vision language models, and also like in the future we also have this kind of like vision language action models that like if you guys read the news, like RTX, like those kind of like big transformers that actually just like you can tokenize the data, and so that you can just like have the big models to actually run on the cloud to help robots to do this end-to-end learning. So we have this new age that we have to use the cloud because we cannot expect our robot to have A100 on the robot, but it's just like somewhere far off from the cloud. We need to be ready for this change. We need to be ready that we like all the robots, instead of like running some like complex ROS algorithms or whatever that is wrapped in the ROS node, but it's actually just like they are issuing like complex like things like web requests, WebSocket requests, WebRTC requests, whatever. But but so that's why we are thinking just like, are we ready for this? Are we ready for just like having all the robots, all the functionalities to do some like end-to-end learning with the cloud? So like, I think this is a very big change to us. It's like we need to make sure that all the like infrastructure, all the like requests being super reliable, because like for the large language models, vision language models, or whatever, like basically it's just interacting with humans. So like, for example, our ChatGPT doesn't respond, we just refresh the web page, I don't care. Regenerate, I don't care. It just wait for another 10 seconds. It's not going to be latency or safety critical. But for the robots, it's totally different. Like because we like human need to interact with robot, and we have no idea what's going on. We have no button like say, oh, refresh the page. And the robot can already just like bump into a certain person or object or whatever, or do some crazy stuff. So wait, hold on a second. I think yes, it's just like so I just like, is it ready for? Are we ready for this? So the the thing is just like, I think just like technically I think we are ready, but we are not that ready, because reliability is a very hard thing to do. So like basically what's really changed from like traditionally, like why did like if we just like move the like some kind of computing resources to the cloud or to somewhere else, like what kind of difficult things that can we introduce? Actually, there are like a lot of difficult things, because uh there are like so many components that is in the middle between the robot and also cloud. No matter like how many switches you establish, like or like this Kubernetes cluster or whatever is like literally sitting next to you. There are like a lot of like switches and also routers, access point that is sitting in the middle between the robot and also the computing resources that you're going to have. And if there's a certain like single point of failure, and the robot stops moving or stops being responsive, responsive to whatever the request you're going to issue. And also, like if the server breaks down, that's also the same issue. Of course, like I think just like generally, I think just on the server breakdown side, I think the cloud is better, because if the server fails, we can certainly reroute the request to another server. But I think in general, we want to make sure that the robot is robust to this kind of like reliability challenges we are going to face. So I'm going to quickly summarize like the 3 points that basically to make the definition to be more clear is like latency reliability, which is basically the reliability that we expect for like for a certain request. Commodity hardware is basically just like we are not running some like very crazy or expensive like real-time systems. But of course, like even if you run this kind of real-time systems, I think you still have the similar challenges. And also single time deployment, basically say, oh, the system has a single point of failure. So I want to quickly draw a parallel thing, like to see like what I'm trying to do is this kind of very well-known theory in computer science is called like CAP theorem, which is the building up an implicit triangle of like basically 3 properties they just cannot coexist, but like that you can just only have like at most 2 properties, and you have like, but you cannot just like have 3 properties that occurs at same times. So basically, we also ask ourselves the same thing, just like, can these 3 properties, latency reliability, commodity hardware, and also single time deployment, can they coexist? And so basically, we just like do some crazy proofs by just like definitions, just like formally define all the terms, like define them in probability, and then just like prove it. And the lesson learned from this is like, commodity hardware, single time deployment, and latency reliability, they cannot coexist. You can only have 2 properties, but not 3. And we can actually find just like all the related work that fall into the 3 categories. Like we have like traditional cloud robotics like framework that's sitting between the commodity hardware and also silicon deployment, because they don't provide technically latency reliability. Like basically you basically hope like everything just works. Otherwise you don't have any just like backups. We can also find a lot of like real-time system community. They just like build up systems that essentially just like do some like fine-grained control on the scheduling to make sure that things are in real time. And so basically we in that case we basically give up this commodity hardware, because like we certainly want to just like make things to be specialized to a certain system or specialized to a certain application to make it work. And also like for this work, or just like the things that we hope to develop is that suppose we give up this singleton deployment. Suppose we can replicate our resources. This is actually one of the advantage of the cloud. Can we make it to be more reliable? So this is a philosophy we want to have, is like, oh, like suppose we increase the number of servers or increase the number of like, of course, they are all failure independent. Suppose we increase the number of failure independent servers, plus we increase the number of failure independent network links. Can we reach the true reliability? And of course, the theory plays pretty well, just like the latency reduces, or sorry, the failure reduces exponentially by just introducing the failure independent servers and networks. Like this is just a very intuitive like example of why this works. So like suppose we just like replicate our resources into 3 times, and then we send a request to 3 different servers and we get the first response. And if of course like if we just like send this request through different links, then it's going to be fully independent, because the 3 requests go through different routes, right? And then just like on the implementation wise, what we do is just like basically implement what I described, which is just like send requests, like in this case, like say, oh, like I have 5G and Wi-Fi. I just have different threads like sending through different links. And then just like, and then I send like for different links, I send to different cloud. And basically the cloud also operates independently. So whenever there is some server or like thread fails, it doesn't really matter. Just like as long as the other threads are still working, then we are still going to be very reliable. So this is the intuition that we want to build up. And of course, like there are like a lot of like optimizers, and also like determine like which server we want to forward, so that we can make sure that everything fulfills the deadline. And also we also have like some kind of connectivity servers that's handling the addresses to make sure the threads are connecting to the right server. And this actually plays pretty well in practice, because if we just like actually align this with the actual thing that we want to do is motion planning. Because for the motion planning, it basically is running RT, random exploring. Basically what it does is to just like randomly sample the points on the space, and then just like just like testing if it's collision free and build up a tree. So why this works in practice is like if you have more threads or more computing power, it's going to just like make the just like kind of random sampling and exploring to be faster. And then just like, for example, this is a task from open motion planning library, which is to just like getting from the target position to the end position. And basically what it does for the motion planning framework is to just like sampling on the action space to say, oh, like how we just like do the rotation, do whatever, and to just like make sure that this like from the beginning pose to the end pose. And then if we run this in a like 96 core like cloud server, it actually just like as you can see, it has a very long tail effect, because we are random exploring, and this goes by probability is asymptotic. So, however, if we have 2 servers basically using our LSC frame, which is just like if these 2 servers have like they just take the first response, and we don't have this kind of singleton deployment issue, and then we are going to see like the long tail effect is almost gone. Of course, like if you increase more servers, it's going to just like getting better and better. Here we only use 2 servers, and as you can see, the long tail effect reduces significantly. We model this by cumulative probability density, and we just look at just like the long tail, and as you can see, it just like basically cut this tail by using 2 servers. And of course, like we just benchmark with like a number of like different scenarios. It just works in the same way. Basically, we just like reduce the latency significantly. And of course, like people will argue with me, oh, like you are using two servers, you are being more expensive. And actually, this is not the case because in the cloud, there is actually a pretty nice pricing model called spot VM, spot virtual machines. We typically see this in, like for example, Google Cloud, AWS, and also Azure. At least the major cloud service providers have this pricing model, which is basically you can just like use those machines at any time, and you are just like having only 20% to 40% of the original conventional like cloud pricing, but they are going to preempt you at any time. So basically, they are going to terminate your machine at any time. If there is any like other user is going to actually use the machine basically at the cloud, basically the cloud price. So this is a pretty good model. Like for the cloud service provider, it's just like they have like some kind of like discounted machine, like basically to just add idle time of this machine. So this actually works pretty well, like for the cloud service providers. But for us, because we have this kind of very fault tolerant like framework, basically just like, oh, we just issue requests to multiple machines and we don't care about whether or not it fails or not, right? So even if the machine fails, we don't really care because like we know that it's on probability, it just like simply just increase like some kind of failure in like, but still the failure reduces exponentially. So in this previous example that I just showed, like we reduce, basically we cut the long tail effect. We also reduce the like mean latency significantly. And also here, we also 2x cheaper than traditional using the cloud. So this is actually a pretty interesting thing. Just like we are cheaper and also we are more reliable. So this is actually a pretty interesting thing that we do. And also there's also another thing we do is just the cloud connected vehicles. So anyone who visited San Francisco, we have this like Waymo thing, right? Just like you basically just works as Uber that you just order on the phone, and then just like you hopefully just like there's a car from Waymo just like drive you and just like get you to the destination in San Francisco, get you around. This is totally like unsupervised until like some kind of emergency that happens, like things that requires a human intervention from the cloud. So there's no safety driver that's sitting in the car, but you rely on some kind of person that remotely to control the vehicle. Basically, just like it's not just like teleoperated, just like giving the vehicle instructions if the vehicle doesn't know what to do. So as you can see, this is actually a very latency critical thing that you want to do from the cloud, because the cloud need to issue the request and do this kind of feedback control loop. And so, and also like, of course, we don't have a big Wi-Fi that has very good network in this case. So we rely on the 5G network. So let's see if we can also apply this theorem and also apply this also in autonomous driving case. So what we do is to just like have our vehicle to connect with both AT&T and also a Verizon. And we drive from Sunnyvale to Berkeley, which is a 50-mile drive. And as you can see, the latency has very large disturbances, no matter what service provider you do. Like for example, in Verizon case, it's basically just like the overall latency is higher, but you have less anomalies. But AT&T is like have higher anomaly, but just like lower latency in general. Of course, this is not an advertisement to a certain service provider, obviously, because like different service provider have different coverage. And also we also have this kind of handover issue if we have high mobility, which is to hand over your request to another base station. And this introduces a service interruption when the car is moving. So what we do is also apply this theorem. Like suppose we use like failure independent servers and failure independent networks. Then as you can see, like it's just smooth. I mean, lighter is better. As you can see, it's just the latency just smooth. It's very smooth. As you can see, it's almost just like doesn't have any like latency, just high latency cases at all. We are actually 3x improvement on the mean latency and almost 4x improvement on anomalous latency by just using this kind of failure independent rate. So basically, just like it's saying, like most of failures in practice is independent, like probability works well. And if you just like want to deploy this kind of failure independent infrastructure, you are going to have very reliable like latency and also application performance. And we also have another one that is following robot across 5G and Wi-Fi. This is actually a case that from our sponsor that they showed to us. It's like they have a mobile that's following the human and do some like things, basically to hand over stuff, like carrying stuff for the human. And they have this issue. It's like in the warehouse, it's using 5G, and if the vehicle go out of the warehouse, it's using 5G. And so this transition actually introduced like some kind of latency whenever they are going to just like move something just like from inside the warehouse to out of the warehouse. And this interruption is just like very annoying because they sometimes go even up to 10 seconds. So basically, just like still, if we leverage this kind of like redundant links, we, as you can see, like the yellow one is actually ours, and we just like we walk across the hallway with just like a different like basically 5G and also like Wi-Fi coverage. We are going to have like much stable latency across this kind of trajectory, and just works pretty well. Of course, for the sake of time, I'm not going to cover what I'm planning to cover. I'm going to just quickly go through the slides I'm going to have. So basically, there's something that I'm also recently looking at is the big data on the cloud. Basically, we have like a lot of data, and robot data is much larger than like things like ImageNet and also things from other fields. So, and also storing such large data sets, it's also very expensive because people typically ignore like the egress cost of the cloud if someone else is going to download the data. So basically what we want to do is to do some compression from the video, and then just like there's already some work that already does it, but it doesn't do it in a very clean way, which requires a lot of like hard-coded semantics on the data and also the format. So, but basically what we do is to just have some kind of format that is inspired by MKV, that is very flexible, and just like here are how the ways that we do it. And by essentially what we do is to just significantly reduce the data. Just like this is original data set, as you can see, it's almost like a 70 times like reduction on the data set size itself. And also we are also significantly both like faster and also smaller in terms of reading. So, and also it just works. And with all the compression, we can also train our policy stably. Just like it doesn't have any funny issues, just due to the video compression. But anyways, let's conclude our talk and let me know if there are any questions. And thank you so
much. Thank you, Eric. I think we'll use the hand queue for any questions. So please put your hands up. And Eric, go ahead and manage it yourself. I won't tell you who's at the top.
Yeah, I think, Grawani, I think you are the first one raise a hand. I think that's how I'm reading this list.
Thank you. So Eric, first of all, thanks for the amazing call and congratulations again for the fantastic work. I really like it a lot because it has all the distributed systems part, the CAP theorem, all the knowledge about cloud computing, the spot instances combined to make robotics better. So really excellent work. But I have one question for you, specifically about the paper where you're showing, for instance, you do motion planning for an arm and you send the request across multiple service instances. Let's put it this way. But I was thinking, to do that, you have to change the way it's implemented, right? Because you have to, as far as I know, the planners are stateful, at least in MoveIt. So you have to somehow implement something like REST, representational state transfer, to transmit the entire planning scene, the kinematics of the arm, or how did you transform it into something that doesn't have state? Because otherwise, you would have to replicate the state across all the instances of the that are responding to your service request, no?
That's a very good question, actually. We actually do a lot of motion planning, so we have a lot of variations. So here are a few experiences we did. So first of all, like for the fault tolerant one, just like the twisty cool, like just like move it, just like for that one, just like for failure independent server one, we didn't do any state sharing. And probability works in that case. Just first response actually works. That they don't need to do any coordination. Surprisingly, just probability just works. And for the other one, for the just like for the one that we had for just like a large number of cores and different servers, we actually just like I didn't present here, but we actually have a work that do it with lambdas, AWS lambdas, and we just like use some kind of EC2 server to share the state. So if you are interested in that one, I can actually send you MP lambda.
Gladly, because yes, I'm always wondering how you, because to me the planner of Move It is a stateful thing because it has this planning sim. It has to know the condition of objects and obstacles that your robot is facing before it can actually plan. So I was wondering how you send this over to the different instances.
Oh, I see. So for that one, we basically assume a static thing. So we don't do any dynamic thing for the motion planning.
Okay, so you just use the kinematics of the arm then, and no obstacles, no planning sim. Okay, thank you.
Yes. Let me see. Christian, you are the next.
Yeah, thank you. Thanks for your talk. I really enjoyed it.
Yeah.
I wanted to ask specifically about the channel bonding that you were using between AT&T and Verizon.
Yes.
So you seem to be doing the redundancy or the mutual bonding at the application level in FogROS. Have you compared that to just doing the Linux kernel supports what is called channel bonding or network bonding, which combines two network interfaces into one, and then you can specify at the kernel level how you want to use them as fallback or just merging them. Have you compared to that? And I guess my question is, when would I use your approach versus doing it at the operating system level?
That's actually a very good question. So first of all, if you're doing it on the kernel level, basically all the retransmission protocols are useless, right? So basically you need to basically implement your own like retransmission protocol to handle this kind of fault tolerant like servers, because you are actually sending two different requests to two different servers. Or just or if you want to send to one server, that you also need to make sure that it's all flexible. So basically, still we need to redesign all the retransmission ones, protocols. And also the second thing, so basically just like if you don't care about retransmission, you just like send the UDP packets. I think that's definitely comparable, but we actually have retransmission. So the second thing is just unfortunately ROS doesn't work. ROS, I mean, I tried with two different DDS, Cyclone and also Fast DDS. Both of them doesn't work quite well if just with just like kernel level, and especially just if you have one link that is down, it just like throw random errors, like things like the interface is gone. Like this is actually a well-known issue on their GitHub, but they just say this is how we architect everything. So so basically just like ROS doesn't work in that case, or especially DS doesn't work. So we try to reproduce what you told, like remember the human following one, we actually try to reproduce that one, but and by the end of the day, just we converge back to just like a map that has like both Wi-Fi and 5G coverage, especially because when just like we try to just like say, like suppose this Wi-Fi is gone, then we just how do we emulate that behavior? But we realize like ROS cannot support it. Yeah.
Okay. Thank you.
Next one is Phil.
Yeah, I got two questions for you. The first, in your slide where you showed sending a request to multiple servers, are you expecting the same response from each of them, or are you okay with different answers?
That's actually a very, very good question. So the answer is both. So we actually have two different models. One is the deadline model, which is to just until the deadline, we accept all the requests, and we just compare with just like high quality one. Just like we manually say, like this is a larger model, so we think this is probably a better, a better quality like response. So we are going to take that one. So basically, we're just getting the higher quality one just until the deadline. So if that's the case, we do differentiate different requests. And also the other one is just like literally taking the first response. Then if that's the case, we don't care about, as long as there's a response back, we don't care about quality. We just, as long as we are happy with the result, we just take it.
So you're not expecting your multiple requests to the hardware to give you the same answer. You're just taking whichever one comes back first, or scoring the different servers and waiting to see the best one you can get. Okay.
Yes.
Interesting. Yeah. My next question, and this is a little bit more for everyone too. You're talking a lot about using multiple networks for reliability, but what happens when everybody starts running all the robots on multiple networks? I mean, aren't we then kind of overrunning our network bandwidth overall?
That's a good question. So I think this do happen. Actually, I can mention a scenario by Cruz when Cruz is still alive. So there was a big concert at San Francisco, and people call Cruz, and all the Cruz cars and Waymo cars just like go there and just like pick people up. But like all the cars are just like dead over there because, you know, just like constantly in the concert, you know, just like everyone is connecting using 5G. And then just like the cellular like base stations, they just like, they are not responsive. So the remote human cannot control all the vehicles. And then the vehicles are just like being dead over there because like stop is their actual fallback if there's no connectivity. So this happens. Honestly, I don't know how to resolve this concert issue. Like even today, I mean, just like no network is definitely doomed for cloud robotics. So I think so. Okay. Let's put it this way. Let's move this to a next step because I don't know how to solve this issue.
This is an interesting question because you raised it to the group. I'll chime in. So one thing that robotics companies sometimes face in warehouses or other customer deployments where the Wi-Fi is spotty is that there's basically areas where the network is good and those where it is not good. And so in some ways you need a technique to either avoid the gaps, right? The outage hole, the holes. And you almost need to either have a gradient where you can realize I'm going towards an outage, so don't do it, like you turn it on. Or you map it. That's a very popular approach where you basically create a Wi-Fi coverage map of your area and then you avoid those areas if possible. In the case of the concert, it might be hard because that's literally where your pickup is, so you can't just drive around it. And then the other one that people implement, which wouldn't work for AVs, but for warehouses is when the robot finds itself disconnected and there's absolutely none of the network connections work, it will use some sort of safe way, like safe fallback behavior, where it will basically go to the last spot where it did have Wi-Fi, or typically the dock. But it's just mention chiming in because it's a very real problem in deployments. So very worth thinking about.
Yeah, and also this actually reminds me of my good old days when I was working on VR, and we also have some kind of like predictive controls also to basically mask the latency between the frames so that user have good experience, and also especially in case of this kind of like glitches on the network as well. Okay, the next one is Michael.
Thank you, and thanks for the talk. As the others have said, it was really interesting. I had a question about whether you've considered using a local model to compete with one of the remote server instances. So we know that cloud is more powerful, but if one or more cloud connections aren't responding, then even a slow connection is better than none. Have you looked into that, and what were your findings?
So just to make sure I understand, so basically we can have a local model that is on the robot and also a cloud model, and basically we do this kind of like we do this kind of first response style like thing, just like take the first response And then whenever there is something that comes back, then we just take it. Is that what you are trying to?
I would say a graded one. You were talking about your other model, because I think the cloud one would be a better response, but almost always slower. If you use a simplified model on the robot, that is.
Yeah, actually, just I think we actually did something, or just my collaborator did something. I wasn't on the paper, so he was doing something on autonomous driving, and he does that. Basically, I can also point you to that paper. Can autonomous driving, can cloud make autonomous driving safer? I think that's the title. Basically, what he did was to just having a big model on the cloud, and also big model on the cloud, and also small model locally. And he did similar stuff. So let me send his paper out in the chat as well. So yeah, I mean, yeah, but basically just like basically we discuss this all the time. So I think especially in this kind of, especially for the safety critical scenarios, we definitely need some kind of like analytical low end things to just mask the latency if the cloud doesn't be super responsive.
Got it. So essentially your colleague tried it and their findings are in the paper you linked. I'll have to take a look at that.
Yes, my colleague looked at it. Yeah, that's a better summary of this. Yeah.
I had a second question as well. For those that don't know about FogROS2, is there a demo or a site you'd like to share that we can send out and make sure people have access to resources?
That's a good question. So I think the repos speak for everything, but let me think. Repo and paper, I think, yeah, I think just that's a very good question, because in past years we don't do any repos on the new FogROS stuff, right? So I think that's a very good question. So probably what we can do is to just search for the papers in the video, and then just like I think just all the just information can be found on the papers. I guess that's an easier way of describe this.
Okay, yeah. I'm happy to take a look. Hopefully we can add those to our resources page, and I'll link the repo as well. Yeah, thank you. If there's any other questions, I'm good.
Let me see. I think that's all the questions, unless I'm missing anyone. Okay, I think that's all the questions we got.